Okay, this is example 2.4, page 56, and this is all work dealing with three forces in equilibrium. So we've already discussed this in class, but if you go to Copeland, the three-force rule for equilibrium, which appears on page 55, which I've explained in class, along with the idea of transmissibility of force, because you need to understand those two concepts to do this type of question. So that's on page 55. If you look at Copeland, the three-force rule for equilibrium states that a body is in equilibrium and has three forces acting on it. If a body is in equilibrium and has three forces acting upon it, these forces must be concurrent or parallel. So that all sounds very complex. It's not really. It's really a matter of learning how to do this type of question. You will need yourselves a geometry set. It's the sort of thing that your parents bought you 100 times since you started kindergarten and you've lost it 50,000 times. They're $7. I got this one at Woolworths. You can buy it really late at night, so there's no excuse to say the shops are closed, blah, blah, blah. Woolworths is open till like 10, 11, 12 sometimes in some suburbs. So go get yourself a geometry set. You will use it all of this year, and certainly if you continue on to year 12, you'll definitely need it. And for these exercises, the thing you need it for is the protractor, but you'll need compasses, you'll need various things when you're doing technical drawing and whatnot. So for this example here, keep in mind that they've explained how to find the point of concurrency. Now, the first thing that I found confusing about this whole idea of forces in equilibrium, three forces, the three-force rule, was that the point of concurrency doesn't necessarily lie on the actual body itself. So that's the first thing to remember, and that's why you need that idea of transmissibility of forces. So for this diagram, they probably wouldn't give you this line here, this reaction line that I'm crossing out, but you'll need it. And they probably wouldn't extend this weight line upwards along its line of transmissibility. So you'd normally get this diagram with just this guy holding onto this rope with this angle here, 15 degrees, and the weight force. And you'd be going, well, that's two forces acting on the body, 1, 2, and yet this thing is in equilibrium. So what you need to say is there must be a third force if it's in equilibrium. So whenever you draw a diagram that's a free body diagram of a situation which is about equilibrium, you will find that if you put all the arrows tail to tip, they will return to the starting point. Okay, so you'll end up with a closed loop. Okay, so for this situation, the first thing they tell you to do is extend your line of weight up. So they would have drawn, they would have gotten their ruler and they would have gone up like that and drawn that line up. Okay, and once that intersects with this line that this guy's holding onto, that is your point of concurrency. Okay, so that's where all your forces are meeting. So we need to say, well, there's three forces acting on this body to keep it in equilibrium. So the next one they would do is, you know that it's touching the earth at this point here, so you would need to say that that's a reaction force. Now you're going, well, is it reacting that way? Is it reacting this way? Is it reacting this way? You'd be saying, well, how do I know which direction it's going in? Well, because it's in equilibrium, they've told you it's in equilibrium, you know that it's going to pass through that point of concurrency. So once you've done that, you draw that line from the corner where it's touching through where your weight force and your tension in your line meet. And by doing that, you've got all the lines you need to solve this problem. Okay, so be a bit more accurate than I was just then, but they've done it in the book anyway. So you've got that line from there to there. So they won't give you the reaction force and this weight force. So we extend your line up first to find that where the 2 points meet, and then go from your ground, where your reaction force is acting, up to this point here. And that is how you draw the diagram. Now then they've turned around and they've drawn a free body diagram from the space diagram, and looking at the explanation, I was going, well, how did they get this 24 degrees? Well, they got the 24 degrees because that's the weight force acting down, and this is, keep in mind, this is an analytical solution. So although that you're doing some measuring to work things out, you're not drawing these lines to scale. Okay, you're just getting the angles correct. So for this particular question, the first thing they did was they worked out the line between the reaction, which is this line here, and the weight force acting down, which is this line here, was 24 degrees. And they worked that out by working out this angle here. Okay, and the way they did that was they put a protractor on that point there, at 0, and they measured what the angle was. So you need to get your protractor onto this diagram, and you need to work out how many degrees and it's probably better to have it not upside down. That will be helpful. What you need to do is measure the angle. So you place a little X on here. You line up your 0 line with the actual reaction line, and then you count up until it intersects with the weight. And you'll find when you do that, if you've got it accurately placed, that it'll come out to about 24 degrees. Okay, so give or take a little bit. So that's how you work out that angle of 24 degrees. You need to measure it with your protractor. And then they've got a second angle in this free body diagram that they've given you, and it's 105 degrees. And you'll say, well, how did they get that? Well, that's the angle between our weight force acting straight down and our tension on our line. That's our tension on our line. So you'll say, if you had the horizontal here, you know that that's going to be 90 degrees, and then you also know, using your rules of geometry, that this angle here is going to be 15 degrees as well. So 90 plus 15 gives you 105 degrees. So once you've done that, you know there's 180 degrees in any triangles. You could actually work out 24 plus 105 minus 180, which gives you this angle here. But they've actually given you the whole angle from the horizontal up, and how they've actually gotten that is they've just gone from the horizontal on your space diagram, and they've just measured this angle here using a protractor. Okay, so that's the first thing you need to understand about how they've actually arrived at this free body diagram that they've given here, because they don't really explain that they've measured those angles, and you might think, well, how have they arrived at those angles? They've just measured them. And then they use the sine rule. If you're good on the sine rule, you shouldn't have too many problems with this. But basically what happens is they say A on sine A equals B on sine B. If you're confused about what's A and what's B and everything else, you just got to remember that in any triangle, if you label the triangle ABC at its vertexes, which is where the lines meet, so we go A, B, and C, then you draw little lowercase letters that are directly opposite the angle. So the C is the actual angle, the capital C, and then you draw a little c here, and you go across here, you draw a little b here, and you go across here, and you draw a little a here. So then you know that the sine of the angle B, this angle here, the B, this side here, is equal to, over this angle, is equal to C over this angle. Okay, so you go from the side to the opposite angle. So in this case, we've got reaction G, which is the force we're trying to work out, okay, which is this line. I'll just show you here a bit closer, which is this line here. So that is a line length, okay. So reaction G, the side RG, over the sine of the angle that is opposite, okay, which is sine 105 degrees, is equal to this side, which is 200 newtons, over the opposite angle, and the opposite angle is this one here, okay, which it's not 66 degrees because it's 66 minus that 15 degrees, so it'll actually be sine 51 degrees. So that's the next question I was asking, well, how did they get 51? Well, they got 51 because 66 is from the horizontal. Okay, so once you do that, you do the maths to isolate RG by itself, because that's what we're trying to find. So we did that by multiplying by sine 105 on both sides, because if the equation's balanced and you want to get rid of sine 105, we write sine 105 here, multiply, that gets rid of it, so we need to put the sine 105 over the other side to keep the equation balanced. And that gives us our measurement of 248.58 newtons. And then you've also got to say to yourself, well, direction, they reference it to the horizontal. Okay, so we know the reaction force is acting up, and we just say that it's 66 degrees, which is the angle that we measured on the actual diagram. And then for the other tension question, we know the tension in the rope is this line here, and so this line, the angle opposite is 24 degrees. So we say T tension over sine 24 is equal to 200, which is the reaction, over sine 51, and then we solve for T. So that's how they've done it. So it's a combination of using the sine rule and also measuring angles on the actual diagram. So the steps to remember are: extend your weight line up till it intersects with the tension line, then look for the reaction force, and you know the reaction force is also going to be reacting so that it goes through that point as well. So we've got 3 points all concurrent. That's the only way we can have our body in equilibrium. And then we say to ourselves, once we've done that, we measure our angles to draw our free body diagram. And as you can see, the free body diagram is closed. It's closed because this whole thing is in equilibrium. So have a go at the practice questions that I give you after this video, and then have a look at the solutions for the problems that I've solved, and hopefully that will be helpful in getting to a solution for this type of problem. See you later.